Yes, yeah, good. So Torben is going to talk to us about so Seagulls Stop the COVID Now.
Yeah, thanks a lot, Hamza. I should say that the title is inspired by a great music video. So if you're bored at some point in your life, I highly recommend watching it. What I want to talk about today is something that I thought about when I did one of my favorite things. I went to the beach next to a fish and chips shop, and I just waited for some people to take their chips, go to the beach, and then open the chips package. And then suddenly, you know, all the seagulls come and try to get the chips. And if we look at what happens on a, you know, kind of simple beach here, so this is a 2D beach. Initially, the seagulls were just sitting nicely, uniformly distributed around the beach, maybe something like this. Okay, and then two people walked up there and brought some chips. And the first one maybe here. Okay, so this is the X, and the second one maybe here. And then after some time, and let's say like a minute, but probably quicker, knowing how greedy and hungry most seagulls are, the seagulls were kind of spread around these two people with their chips. And if one looks at this from a kind of big picture, we do have a nice distribution of seagulls around these two people. Maybe something like, you know, these are supposed to be the contour lines. It doesn't have to be Gaussian. It's just some distribution. And so I was thinking, well, that is very interesting. So the seagulls are kind of some samples that then, you know, follow some distribution after some time. Maybe we can use something similar to estimate arbitrary distributions. And it turns out that this is the case, and there has been a little bit of work on that, but in my opinion, not enough work. So that's something that I recently started working on that for. So to look at a kind of general distribution, we just take the very same distribution. So it looks something like this, right? This, say, and if we think of COVID, then we might have one variable being the reproduction number, and the other variable might be something like the number of social contacts that we might have tomorrow. And we earlier heard that this is a, you know, very simple model, but these variables do somehow pop up. And in that case, what we're interested in are different scenarios, and here's a little pun, I call them scenarios. Okay, nice. Okay, so again, we want different scenarios that could be sampled from this distribution, and we don't want them all to be concentrated in the middle, but we want them really to follow this distribution, so as if they are a random draw from this distribution. And to get the sample, the idea is to start with the uniform samples. So as in the, you know, seagull example, we have these seagulls just sitting around, and then we want to somehow have some notion of time to then, after some time, have these initially uniformly distributed samples following this distribution that we're interested in. And now the obvious question is, well, how could that ever work, right? So let's look at what the seagulls do. The seagulls do two things, and seagulls are not, I don't think they're the, you know, smartest birds. So they have two things that they really only consider. The first one is get to the chips. So this is them being hungry. Okay, so this is very important. And the second thing that they want to do is don't hit other seagulls. This is essentially because they don't want to die by crashing into one another. And how does that look in a general situation in this distribution? Okay, and careful here, general situation, okay, because we're at the beach. What corresponds in the general setup to this, you know, the seagulls want to get to the chips? It's these samples should somehow get to regions of high probability. Okay, so this is then going where the chips are. This is going where the density is very, very large. And the second thing will correspond to the seagulls avoiding each other. So different samples kind of pushing and repelling each other maybe. So this is indeed the second one that I'm going to call just, stay away from other samples. Okay, and if we want this to make this a bit more rigorous, then what we want to solve is the following minimization problem. We want to minimize over D, and D is the set of our samples x1 to xn. So we want to find an optimal arrangement of samples, and we want to minimize the sum over I greater than j, both ranging from 1 to n. The following thing, q xi, q xj. This will be corresponding to the regions of high probability or to the chips, and then over the distance xi, xj. Okay, and then take that squared. Now I should tell you what q is. Q is in this complicated form, it's f. So f is the density of the distribution that we're interested in, and we take that to the 1 over 2pth power, where p is the dimension of the domain of the space. Yeah, this is essentially what the seagulls are doing. This is how one can sample from these general distributions. This approach is called the minimum energy design approach, because one minimizes something that can be viewed as an energy. And then there are some interesting modifications of this method. So one obvious question is, how do I solve this optimization problem in the first place? Another question is, what distance do I use? Another question is, should I use 2 here? Should I use some general k here? Or are there generally better energies to use? And that's something that I'm currently investigating. I don't really have many results there yet. If anyone has any ideas, I'd be very interested to hear them. And yeah, I was now going to sing this song for you, really, that motivated the title, but given the time, I think I just stop here and take any questions if there are any.
Okay, thanks, Torben. Yes, other questions for Torben. So let me, if you go to the slide, I mean, you stopped sharing, so we can't really ask you.
Sorry, I'm just going to quickly share again. Yeah.
Okay. So how, I mean, is this form, why do we multiply q of xi, q of xj? I mean, where is this kind of cost function coming from, really? I mean, there are many ways that one can encode 1 and 2 in a.
Yeah.
Why do you multiply q of xi times q of xj?
Yeah. So the first thing that is interesting to note is that if q is just constant, then this corresponds to finding kind of minimum packaging setups. And there is this conjecture really only that if you use exactly this form, multiplying these two q's of xi and xj, then as in the limit, so as n goes to infinity, we get that the kind of empirical measure converges to the distribution pi of interest. And there are some proof ideas for that, but there's no rigorous proof yet. So
what is the distribution of interest, the pi that you're talking about?
So pi would be, so in this example, this would be pi.
I see. But how is this defined? I mean, in terms of f, you have.
Yeah. So pi needs to admit a density, and the density is given by f of x.
Oh, I see. Okay. So in the Seagulls example, that would just be kind of you rack 2 masses on the chips, or what?
So in the Seagull example, I would argue that there's kind of a uniform prior and then a likelihood centered around these 2 observations that we have, if you want. Okay. And so the posterior, or the distribution that we're interested in, is some kind of multimodal, bimodal Gaussian mixture or something.
Okay. Okay, good. So other questions. So Q&A. Let's see. Okay. So someone said I wasn't quite sure how this related to COVID, but I think that's okay. Yeah, because your thought is stop the COVID now. I mean, is there a connection with COVID?
Yeah, so my idea is to use this approach, but first to kind of work on the theoretical analysis of it a bit more, because I think there are some very important steps missing, and then to apply it to problems. And one example is estimating kind of the reproduction number or other statistics of a pandemic that we can then use to inform policymaking.
Okay.
But I think
more long
term talks about it already. So.
Good. So actually, let's see, how are we on time here? It's okay. Actually.